Levenspiel plots are an important tool used by chemical engineers in industry to estimate the volume of the reactor that will be required for a particular reaction under certain conditions to obtain a desired conversion. And I'll work through this, but the point that I'd like to work up to is showing you how we are able to visually see what reactor type we would need to use based on the kinetics we have been given by the chemists. So in industry, the chemists will discover or come to you with some kind of rate law that tells you that the kinetics behind creating some kind of product C, for example, and your job as a chemical engineer is now to figure out which of the three reactor types, CSTR, BSTR, or PFR, should you go with to actually economically produce what the chemists have come to you with. And there are several things we need to consider. And cost is also a factor in all these. I'm not taking that into account yet. If we assume that cost scales linearly with the volume of the reactor and your objective is to minimize the volume of your reactor, then the main calculations you'll have to do will end here. But there are so many variables at play in the real world that even on paper, it's still going to be a lot more complicated than I'm making it out to be. And so to start off with, the conditions that we typically need to consider are whether or not something's isothermal. Being isothermal is important because whether or not the temperature changes over time or throughout your reactor dictates whether or not the volume of the reactor can change, and it also will affect your rate law accordingly based on an Arrhenius expression. So to start off with, early on in reactor design classes, we assume everything's isothermal to keep things simple. The next question is whether or not you're dealing with an isobaric constant pressure or an isochoric constant volume type of reactor. And you only need to consider whether or not something's isobaric or isochoric in the context of compressible fluids. So when we are working with gases, now you need to consider whether or not you have a volume expansion or contraction occurring as your reaction proceeds. And this is something that you can derive from stoichiometry tables, which I was going to go into, but I didn't want to make this video too much. I'll probably make a separate one for that. Essentially, what happens is if we have a reaction involving gases and the moles of product end up being more than the moles of reactants, and we assume everything's an ideal gas, what will happen is as that reaction proceeds, we're going to have an accumulation of moles of gas. So a larger volume will occur if we are working in an isobaric condition, or a higher pressure will occur if you're working in isochoric conditions. And when you have a volume expansion under isobaric conditions, this has consequences because as your volume increases, you now have to take that into account into your changing concentrations. So as the volume increases, your concentration is defined to be the number of moles of reactant you have per volume. The volume term is increasing, so your concentration is decreasing. And that can have the effect of slowing down your reaction if your rate law is dependent on the concentration. And it can also speed it up too in certain situations. So everything is very dependent. All these variables are very dependent on each other, and so keeping track of everything and staying organized is very important when you are a chemical engineer trying to figure out what is the most effective reactor type to go with, what volume you should go with. and what kind of conditions you want to sustain. So I will say, for reactions that involve only liquids, you do not need to take that into account, because liquids will assume, for the sake of simplicity, that they are all the same density, and consequently we don't have to take into account any volume expansions or contractions, which makes our life much easier. And so when a chemist comes to a chemical engineer with a rate law, and the rate law is something that is determined experimentally. It is not something you can ever derive from the stoichiometry. So just because I tell you A moles of A plus B moles of B react to form C moles of C, this does not necessarily imply that your rate is proportional to the concentration of A raised to the A power times the concentration of B raised to the B power times some kind of rate constant. That is not necessarily the case. You can never make this assumption unless you verified it experimentally. A chemist will do this will run experiments for you and come to you with this equation. It may be like this if it's considered an elementary as written, and in that case we can draw this conclusion, but if it is not, you cannot make this assumption. You have to be given the rate law. And so typically in engineering classes, you're going to be given the rate law you're going to be working with, so you won't have to deal with any of the stuff that the chemists have to work with. But it is also good practice to verify results in practice as well. And so depending on what kind of reaction order we are working with, that will dictate what kind of reactor that will best suit our purposes if our primary goal is to minimize the volume needed. And so when we work with positive order kinetics, our goal is to ensure that the concentration of your reactants is as high as possible for as long as possible. And so the way conceptually a CSTR works is, once the inlet feed comes in, the inlet concentration of your reactants is very high, but as soon as it enters your CSTR, everything becomes homogenized because of the propeller and our assumptions. And because of that, when you want to have higher conversions with positive order kinetics, so this is a graph of positive order kinetic Levenspiel plot. The problem is your concentration of reactants becomes increasingly dilute the higher your desired conversion is. So if you wanted to have 99% conversion of A in your CSTR reactor, the problem is that to achieve that desired conversion, your outlet flow will have 0.1 times the concentration of A naught, and so of your inlet concentration. And so the problem with that is, because we're assuming the CSTR is well mixed, that also means that your outlet stream has the same exact concentration as your inlet stream. So inside the reactor, just like the outlet stream, inside the reactor you have a concentration of reactant that is only 0.01 times your inlet concentration. And so because of that, you have very few moles of reactant floating around to actually react. And so you end up getting very large required volumes, very slow or very long residence times to achieve equivalent desired conversions that involve positive order kinetics. Whereas when you work with a plug flow reactor or a batch stirred tank reactor, as we travel through our batch stirred tank reactor, we assume that if you take a slice at any point within the plug flow reactor and you examine it, you'll find that there's perfect mixing radially, but not axially. And because of that, we do not have to worry about the reactant molecules becoming dilute as they travel through the plug flow reactor, assuming that it's an equimolar reaction of ideal gas. So the number of moles of gas are not changing, your volume's remaining constant. The only thing we have changing, the only the main goal to understand here is that the PFR will maintain a higher concentration of reactant molecules for a lot longer than a CSTR will. And because of that, you do not need as big of a volume for positive order kinetics. And so the next question is sometimes, so positive order kinetics, negative order kinetics, and then we have something here that is a bit strange. You can have, so experimental data will come to you, and this will be easy to plot. Just do it in Excel, and you can derive graphs that look like this. And in this case, for a Levenspiel plot that ends up looking like this, you will be much better off using an in-series 2 reactors. So if we use one CSTR to get to the point where your rate RA is at a maximum, so the plot itself, it becomes a minimum because it's inversely proportional to it, the volume you will need visually is just this rectangle under the curve. Whereas if this was a PFR, we would need to include this additional volume, and you would need a larger reactor. Now, so this is because it is negative order kinetics for the first regime of this reaction Levenspiel plot. But when we travel into the second regime, what we see is that we now have positive order kinetics. And so a PFR at this point would now be an excellent choice to go with, because if instead we decided to go with a second CSTR, we would need this additional volume here to accomplish the same final conversion of our reactants. And so that's the reason why using reactors in series in industry can save a lot of money if assuming volume is directly proportional to cost. And that's another reason why Levenspiel plots come in very handy in the engineer's toolbox when determining what's the best kind of setup to have to maximize yield and do it as efficiently as possible. And we can derive the math equations for our CSTR required volume and our PFR required volume here. What we notice is that the CSTR volume is simply, it's a multiplication of the area of the base, or this is the height times area, so area is just length of the base times the height, and so there are no integrals here, and the RA is evaluated at the exit conditions of our CSTR, like I said before. The volume required by a plug flow reactor or a BSTR to achieve equivalent conversion for the same volume would be equal to an integral of dxa over minus RA. Minus RA is your rate law, and you will need to rewrite that in terms of XA based on the relationship here. But it is important to note that you can only define your rate of conversion like this if you have V naught equal to V, and I denote volumetric flow rates with a dot above them, only if this is a constant value. So XA is defined to be your inlet minus your outlet, your inlet minus your outlet divided by your inlet. And you can think of it like an efficiency term. How many moles of A did you actually react divided by how many moles of A you fed. If you didn't react any moles of A, your outlet molar flow rate would be 0, and so would be equal to FA naught, so we would get 0 in the numerator. You would have 0 conversion. If we reacted 100% of the moles of A coming into our reactor, we would have no moles of A in our outlet here, and we would have a conversion equal to 1. So it's bounded between 0 and 1. And something that came in handy on our homework for our chemical engineering class was, given a rate law, we needed to find out how many CSTRs we would need to use in series, because we had a budget of X number of liters to determine to obtain a certain conversion. And so what we can do as chemical engineers is, given the rate law from a chemist, we can substitute in 1 minus XA, and then we can plot. So we can create a Levenspiel plot in Excel. It won't be terribly accurate, but it will at least give us a good rough estimate. If we plot in Excel the value of FA naught, this is a constant, divided by RA written in terms of XA versus XA, so you would create one column XA, and then you would start it from 0.01 to 0.99. If you take it all the way out to 1, you would get a divide by 0 error. So you would have that be your X column, and then in your Y column, we would plot, or we would compute in Excel the calculation given this conversion, which what does the value of FA naught over RA equal to? And then once you obtain a scatter plot, or a scatter plot in Excel, you could add a trend line, make it a 6th degree polynomial, and from that equation, it's very easy to compute the integral of, which would tell you the volume required to obtain a certain conversion. And I hope that may help some people with their chemical engineering homework. And just to sum up the main point, assuming we are working with negative order kinetics, CSTRs perform the best, because if we look at this example here, of this Levenspiel plot, the volume graphically required by a continuous stirred tank reactor will only depend on the RA at the exit, and because of that, you'll only need a very small volume CSTR, whereas if we use the plug flow reactor for the same reaction given the same kinetics, we would need all of this additional volume, which would add cost to the project. So yeah, I hope you guys find this useful, and let me know if there are any questions, and thank you for watching.